let me start with the journey through the milestones in the perception of the universe. So we all know that a starry night is usually termed as a very romantic backdrop. But beyond that, for the curious people, those who are more curious and those who are more logic or scientific, there is a lot more to ponder on it. We can say that the first systematic or so to say scientific theory for because there were very other stories which were not that scientific earlier. So the first systematic scientific theory for explaining the observed night sky came in the form of a geocentric model of the universe. So later on, this was proved to be wrong, but at that time, this seemed to be very right model for the universe. And you should also remember that the universe at the time meant nothing more than the solar system and the stars. So there are, I'm just mentioning about the two theories, two earlier models regarding the universe. I have put the universe in the brackets because it was actually the model of the sky only, not the whole universe. So we had a lot more beyond the sky. But at that time, they were not having any instruments, so whatever they viewed, they made it into a model. And first person who did it is Ptolemy, and he did it through his book, the Almagest. Actually, all the information which he is giving in this textbook is not by himself, but he has collected it from ancient Greek information, Greek knowledge, as well as Babylonian knowledge. He has consolidated everything which were known up to that time. This was done in the 1st century AD into a book called the Almagest. And the Almagest gives the geocentric model of the universe. The geocentric model of the universe was almost universally accepted until the appearance of a simpler heliocentric model during the scientific revolution period. And Nikolai Copernicus was responsible for the correcting the model given by Ptolemy. Their life spans are given in the bottom. This Nikolai Copernicus was able to correct this model into the heliocentric model of the universe, where the sun was considered to be the center of the universe. So still, please remember that the universe doesn't mean the universe what we think about now. It is just the sky, whatever is seen on the sky, because the telescopes were not used at that time until Galileo. So the Copernicus published his book on the revolutions on the celestial spheres in 1543, just before his death. And this was all very risky to say that the sun is at the center of the universe, because till then the Ptolemaic model had been accepted by everybody, and all the religious beliefs were all connected with that. So to say that the sun is at the center was a very kind of at times it may be a blasphemic thing. So until his death, he didn't publish his ideas, Copernicus. And in 1543, the book was published. And just a mention about a few things regarding the two models. This is just a cartoon of what the geocentric model of the universe says. The geocentric model of the universe, which is by Ptolemy, says that the Earth is at the center of the universe, and the Moon, Mercury, Venus, Sun, Mars, Jupiter, etc. are revolving around the Earth, and only planets up to Saturn were known at that time, and the stars were seen to be or depicted to be very far away. That is why they are looking very small, and they were thought to be occupying a circular orbit like this. And all these objects were moving in circular orbits, because that was some stipulation which was brought in by Aristotle. So the perfect spheres, because all these being made of God, at that time they were thinking like that since all these celestial objects are from God, everything should be perfect. So the planet should be exactly round, and also the orbit should be exactly circle. So then there was a problem that the luminosity of these planets were changing as a function of time. That shouldn't happen according to Aristotle. So in order to explain that, Ptolemy found another explanation, or so to say an escape, I should say, by telling that these planets are not revolving like this in a circular path, but it is actually having a circular path over the trajectory. So like this, this is the orbit, and this goes around this. And this kind of a motion is called epicyclic motion. I have described it over here, epicyclic motion. If this is the actual orbit, then the planet will be on a circle like this. And it was postulated that all these circles are forming a part of a sphere. This is a two-dimensional thing. So we can assume that Earth is there and there is a sphere which is surrounding the Earth, and this moon is stuck on that sphere and it revolves around the Earth. Like that. That was the model. And this is the geocentric model where the Earth is at the center of the universe. And the epicycle was also brought in order to explain it in terms of, in unison with what Aristotle has said. Now, after almost 16 centuries, that happened in 1st century AD, and for 16 centuries, that model, the Ptolemaic model, was accepted by everybody. And after almost 16 centuries, I have already mentioned that in 1543, in a book, Revolutions of the Heavenly Bodies, Copernicus proposed that the sun is at the center of the earth. And this is, in scientific history, this is termed as a Copernican revolution, because that was a very revolutionary idea. And still, since Copernicus also wanted these orbits to be circular, he also had to resort to this epicyclic model, but he put the sun at the center. Ironically, the idea of a sun-centered universe was not a new one. It was suggested by Aristarchus of Samos during the 2nd century BC, but at that time, nobody did believe him, and people thought that he was crazy. But now, Copernicus was able to put forth this new idea that the sun is at the center. And then all these planets are revolving around the sun like this. So this idea was, and the stars, as earlier, it also occupied a farthest orbit from the sun. That was the model. So even this is a solar system plus the stars, not more than that we know for sure. And then the motion of some of the planets were found to be almost like wandering in the sky, and that was that wandering nature was also explained like this. This Mars was this is Earth and this is Mars. If you look at Mars, which is slower than the Earth, then its projection onto the sky will be like it will be moving somewhat like this. So the kind of peculiar motions of the planets also could be explained. That is called a retrograde motion. Now I am mentioning the next milestone in understanding or perceiving the universe in the form of Kepler's laws. So the Johannes Kepler was an assistant to Tycho Brahe, who was a very famous astronomer at the time. But obviously, Johannes Kepler was more brilliant than his master. And his master also, even though he was a very strict guy, he passed away very early in his prime age. And all this data which was there, which was not accessible to Kepler earlier, he got all the ideas and he worked on it. And actually, these three laws of motion of planets are a very important milestone in understanding or perceiving the universe, because these laws are applicable even now when people are calculating the mass of the supermassive black hole at the center of galaxies. They are still using these Kepler's laws. So these Kepler's laws are applicable even now. So these three Kepler's laws actually occupied the whole life of Kepler. It is said that the last this theory, he could formulate this law with almost like taking 10 to 15 years, or 10 years, I think. 10 years he spent on this particular law. And the law says, the important milestone, I should say, is in the fact that the orbits he assumed, or he proposed that the orbits can be non-circular. See, the Aristotelian view that the orbit should be circular was floated by Kepler, and he said that in his first law that the planets are moving in elliptical orbits, and the sun is at one of its focus. And also, second one says that since the planet is in an elliptical orbit, the planet, when it comes nearer, it will be faster, and farther it will be slower. That is the equal-areas, this second law. And the third law, is regarding a connection, an equation. And in that equation, the planet, when it moves around the sun, it will take the time taken by the planet to move once is called the time period. And the length of this line connecting two centers, we have mentioned here one focus and another focus. If we connect these two centers, then we will get a line, and half of that line is called a semi-major axis, and this length is a. So he in his third law says that t square is proportional to a cube. It's not equal to, but proportional to a cube. So the time period square is proportional to the semi-major axis cubed. So this is his third law. And all these three laws are still applicable to any body which is revolving around a central object, in any celestial object revolving around another celestial object. These three laws are applicable. Okay. Now, this is a very important milestone. And then we are coming into the next milestone that was by the observations of Galileo. And this is the first instance when an instrument was used for observing the sky. You might be familiar, this is a telescope. This is the telescope which was used by Galileo for observing the sky. So in schools, there is an erroneous teaching that Galileo did invent the telescope. That is not true. In fact, that was a first telescope was invented by some spectacle maker by name Hans Lippershey. And when it came to the market, people were using it for observing faraway objects or faraway ships. Kings were using it for observing faraway ships which are coming and to look whether and see whether it is a ship from a country in rivalry with them. And then this telescope which was available in the market was acquired by Galileo. He, being a person who is interested in skies, he thought, why not use this telescope for observing the sky? And that was a real milestone in understanding the universe. So whatever was not available for perception by the eye could be seen by Galileo. So this is the original Galileo telescope, and he could discover the Jupiter and Jupiter. This is not exactly true. The Jupiter's moons. It should be he could discover some of the Jupiter's moons. And this telescope is there in the museum. And Galileo's observations were capable of adding much to what was observed through naked eyes. So this is a summary of what new things did Galileo observe through his telescope. What he found was the moon, which was observed to be, or which was postulated to be a very perfect sphere, is not exactly a perfect sphere. It has got this kind of uneven surface like this, and this is his own drawing of the moon, what he observed through the telescope. So that through our eyes, it is not observable. Then Galileo did observe the moons of Jupiter. There were 4 moons of Jupiter which were not visible by visible to the naked eye. The Jupiter was visible. So this is his own depiction of what he saw in his notebook. So this larger circle is the Jupiter, and these 4 are its satellites. And he also found that these satellites are moving around Jupiter in a matter of a few hours. So he plotted all of this. And the name of the moons are Io, Europa, Ganymede, and Callisto. The Jupiter is having many moons, but the brightest ones he could see at the time. And then he saw the phases of Venus. Phases of Venus we are going to explain. And he saw the sunspots. There he observed that the sun is having some spots on its surface, and that spots are moving. So that gave Galileo the idea that the sun will be rotating. And then he found out that the sun is rotating in a period of one rotation is completed in a period of 27 days. And then because of this, you might if you go to the history, you will understand that at his prime age itself, Galileo lost his sight, because now every one of us know that it is harmful to look at the sun, but he was not knowing that. So he was observing all these sunspots, and he got blind later on. And then he has seen the Saturn. Saturn was visible to the naked eye, but when we looked it through the telescope, then he saw that there are 2 appendages, ear-like structures for the Saturn. And you can guess that that ear-like structures are actually the rings of Saturn, which is usually not visible through our naked eye. So the first observation of a ring structure was made by Galileo, but he didn't understand that is a ring structure, but he thought it was some appendages to Saturn. Then most important thing, so to say, was that he could resolve the Milky Way, the white patch of light which is visible in the sky, as containing a large number of stars. So we are coming to the Milky Way later on. And the Milky Way is sort of a patch of light which is seen on the sky, which is actually our galaxy. And by naked eye, we cannot separate out the stars which are constituting the central part. The other stars we can see. So this central part, this patchy kind of central part, he observed through the telescope and saw that all the stars are very densely packed over there, which is not visible to the naked eye. Now, just I'm mentioning about this the phases of Venus. This iconic look at the sky through the telescope actually supported the Copernican model like anything. So let us look at the 2 scenarios. One scenario is Earth is over here, and you might remember in the Ptolemy's model, Earth is at the center, and the Venus is moving like this, and Sun is farther to the Venus in the geocentric model, if you remember it correctly, the first slide. And then this Venus is also not moving in an orbit like this, but it follows a epicycle like this. That also we mentioned like this. And then if this is the case, then the Venus, when it is very far away, since the Sun is on the other side, this would appear darkest when it is farthest from the Earth, and it should be smallest. But actually, when Venus was observed by Galileo, he found that when the Venus is far away from us, then the Venus is totally bright. So this could only be explained if the Sun is at the center and this Venus as well as Earth are moving around the Sun. If this is the scenario, then you can explain while looking through from the Earth, we should see when the Venus is farthest, it should be full moon, full Venus, like the full moon. So this is actually when he observed, he saw this. So this was a solid proof to the Copernican model that the Sun is at the center. If that was not the case, then we should have looked, the Venus should have looked like this, completely dark, but it is completely bright when it is far away. So that is one of the major kind of contributions from the Galileo's observations. Now we come to another milestone, which is regarding the Newton's law of gravitation. Newton's law of gravitation, which is another milestone. You all might be familiar with this Newton's law, wherein if we have two masses M1 and M2, then they will be attracted towards each other by a force, and the force is given by this. And this attraction is responsible for our Earth to be remaining as a sphere, and the Sun to be remaining as a sphere, and the Earth going around the Sun. The reason for that is also can be traced to the Newton's law of attraction or Newton's law of gravitation. And all the stars like the Sun are consolidated into something called our Milky Way galaxy. That is because the stars are being attracted with each other due to this theory of this law of gravitation. So this law of gravitation is a very important milestone in the development of a perception of the universe. So this attractive force, when it was suggested by Newton, this was instrumental in explaining all sorts of structures like the Sun, Moon, the Earth, and also the galaxy, everything required the presence of a gravitational attraction between celestial bodies to form such structures. So this is a very important milestone in the perception of the universe. Now we come into another idea, like Messier. This is Charles Messier. What he did was, there was other than the stars, nearby stars, there were also, when people, scientists looked through larger and larger telescopes. I didn't mention, after Galileo, there was a kind of a passion for making telescopes among scientists, bigger and bigger telescopes. And when scientists look through bigger and bigger telescopes, they should see the more from the sky. So rather than stars, which we usually see, scientists started seeing some fuzzy objects, some patchy kind of objects, bright objects on the sky. And some of them were observed to be comets, which is explainable. And there were also some confusing objects, which were not really comets, but they also are there in the sky. So this was thought to be a part of the Milky Way, part of our solar system. And then this Charles Messier, what he did was, he just wanted to help the comet hunters. The comet hunting was a sort of a hobby at that time, among the sort of a hobby for the scientists, or most of the astronomy people were trying to hunt the comets, to find new comets and all. You know, the Halley's comet, etc. So this was the case. So what Messier did was, he just wanted to catalog all these fuzzy objects into a particular catalog. And the catalog name is like this: Catalog of Nebulae and Star Clusters. And this he intended as a guide to comet explorers. He can say that all these objects are a nebulae. These are not comets. So don't misunderstand this for a comet. That was his idea. But originally, what he mapped was the galaxies, which are most of them turned out to be galaxies which are outside our galaxy. He was not knowing that. He was thinking that this is some object which is a part of our solar system. But it is not. It was not actually like that. This was very large galaxies which are at very large distances. But when we are seeing it, it is seen as very small. You understand that we can see a very large house which is far away, in between two trees, maybe 1 meter across, 1 meter aside. in front of us. If we have two trees in front of us, and if you look through in between the two trees, if there we can even see a very big house in between that. But it will be seen as a very small house. Like that, what he was seeing was very far away galaxies, which are seen in through the in between the stars which are there in the Milky Way galaxy. So that's why they looked very small and patchy. So final version of this his catalog, which was presented here in the French Academy, contained almost like 103 objects, and later on the number somebody added some more objects into that, and that was in 1781. So some of the members of the Messier catalog, the first member M1 is not actually a galaxy, but it is an exploding star which is in our galaxy itself. But it was also seen in the sky when he looked at through the telescope, and he just thought it to be some fuzzy object, and he marked it as M1. And M104 later happened to be a very large galaxy which is in the neighborhood of our galaxy, and this is seen in the sky as like a small patch. So this could be seen like this only when this was observed through larger and larger telescopes. Okay. And then there was more bigger telescopes made by William Herschel. And William Herschel was also trying to watch the sky through a more better telescope. And then he also made catalogs, a catalog of a second 1,000 new nebulae and cluster of stars, etc. So he was mapping the stars as well as nebulae. So these patchy objects were termed as nebulae when people didn't understand what was it like, what was originally a nebulae. And then this William Herschel's most important milestone, using his instrument, this is the instrument responsible for this. What he did was he made the first map of the Milky Way. So at that time he was not knowing that as probably as at that time maybe he knew, because Galileo could decipher the stars in the Milky Way. So each and every star which is a part of a Milky Way, which he could observe through his telescopes, and we can see that this may be only a few thousands, and our galaxy originally contains 2 × 10⁻11 number of stars. So what he got is a very, very tiny portion of the whole number of stars. Only the brightest stars which are very nearby us could be mapped by him. But even then, this is a very real milestone. Like, he was the person who could just make this kind of a shape. This is not the actual shape, but this kind of a shape for the galaxy, so the Milky Way galaxy. And he placed the sun at the center of the Milky Way galaxy, which also will be proved to be wrong later. But even then, some of these things are erroneous. This was also another milestone. Now coming to the next milestone is in formulating a method for measuring the distances. That was done by none other than Henrietta Leavitt, a woman astronomer, American astronomer. At that time, only a very few women were in astronomy, but she was one of the pioneers among the woman scientists, and she did contribute a very important milestone to the perception of the universe. That is through her period luminosity relation for Cepheid variable stars. She observed some stars through the telescope and found that their luminosity varies as a function of a few days. And then she connected this period of variation with the luminosity. And this connection brought in a method for finding out the distance to the stars. And this was used for measuring distances, and that was in 1912. This eventually became the key to measuring the distance to galaxies. In 1917, another development did happen. This scientist by name Harlow Shapley, who is also an American astronomer, he studied our galaxy. Until then, it was believed that our galaxy is almost like 1,000 light years across. I'm just coming to what light year is like in the next slide or so. But when he measured, he found that our galaxy has got 1 lakh light year of expanse. Our galaxy measures from one end to another, 1 lakh light years. We'll see the image of our galaxy very soon. So that will be more clear over there. Now we come to another milestone in which this Harlow Shapley is sort of a person who is involved, and we see him as a different person because he is at a larger age at the time. So this is the same Harlow Shapley, and this is Heber Curtis, and they had a very famous in the scientific circles. This is called the Great Shapley-Curtis debate. So this is the Great Debate. This is known as Great Debate. And in Great Debate, these two people made a debate, scientific debate, and the subject matter of a scientific debate was I'm a little stuck now. Maybe let me see to move this. Yes, moving. Yeah. And ironically, this is the sort of 100th year of the Shapley-Curtis debate. It happened on 26th of April in 1920. Now, this April, this debate did complete 100 years of its existence. So, the great debate, also called the Shapley-Curtis debate, was held at 8:15 p.m. on 26/4 in this particular hall, and it was focused on the uncertainty about the extent of our Milky Way, whether it constituted the entire universe or the debate was whether the Milky Way is the whole universe or these small patchy spiral kind of objects which were seen as a kind of nebulae, are they galaxies like us, like ours? That was the question. So actually, Curtis was of the opinion that these are all these small patchy kind of things might be other galaxies like our Milky Way, but it is seen as a very small because they are very far away. But Shapley didn't believe in that. Shapley was of the opinion that all these our Milky Way galaxy contains all these patchy elements. Everything as a whole is the whole universe. And this argument did take place. And Curtis argued that there were other independent galaxies, implying that they are exceedingly large and distant. But Shapley was believing otherwise, and this resulted in two papers. And later on, we can understand that Curtis was proved to be right, because all these patchy objects were found on the sky was found to be other galaxies like our Milky Way galaxy. So that was done by none other than, or these patchy objects which were seen on the sky, very small patchy objects, were found to be galaxies like ours by a famous scientist by name Edwin Hubble. So what he did is he used some of these patchy objects, or what we call as a nebulae. He took the photograph of nebulae using a telescope, and then he had seen that this nebulae, this hardly seen here, this is our neighboring galaxy Andromeda. And on this Andromeda nebulae, at that time it was called Andromeda nebulae, and it was known to be a galaxy. And he has spotted some variable star in this galaxy. This galaxy is extending to this much area. And actually here it is not that much clear, but the galaxy extends here also. Not galaxy, at that time it was called a nebulae. And inside this nebulae, he observed one particular star which is having variation in its luminosity, and he later found it to be a Cepheid variable. The Cepheid variable is the kind of stars which were used by Henrietta Leavitt to measure the distances. So an idea came to his mind: why can't I measure the distance using the Henrietta's method? Then he measured the distance to this star by using the Henrietta Leavitt's method, and he got the distance. And this star is a member of this nebulae. So if we measure the distance to this star, then what we are actually doing is approximately we are measuring the distance to this whole nebulae from our Earth. So to his dismay, what he has obtained is that the distance to this nebulae is larger than the extent of our galaxy. The extent of our galaxy was found to be 1 lakh light years by Shapley, and the distance worked out to be more than that. So what does this imply? It implies that actually this Andromeda nebulae is outside our galaxy. So it may be like our galaxy, it may be another galaxy. So he said, or he postulated, or he proved, or he observed and proved that this is these nebulae are, most of them are nearby galaxies. So this image, even though this doesn't seem to be much pretty, but it opened a great door for the first time in humanity to gaze into the vast universe. So we are starting to see beyond our galaxy. So the Shapley's argument is wrong. Rather than our galaxies, there are also other galaxies. What we see as a nebulae are all other galaxies. So the next thing what he did was to use his telescope to measure the distances to such different nebulae. We mentioned that Messier has listed many nebulae, and using his telescope, this is his historic telescope. So I always would like to show the instrument which was used, but because the theme of this talk is how the instruments actually helped scientists to perceive the universe in a better way. So this is his telescope, and this is the largest refracting telescope existing now. This is also there, it's not being used, but This is the largest refracting telescope. It had it's a 100-inch telescope, means it contains a lens which is of 100-inch. 100-inch is almost like a 2-inch is see, 2 centimeters is 1 inch, no? So likewise, so we can say that this is a big telescope at that time, and it used lenses. This is the largest telescope which uses lenses. Okay, so this was almost in 1922. This is Edwin Hubble doing his experiments, making his discovery, and this was a solid proof for the idea of external galaxies. And that Curtis is actually true, not Shapley. Curtis was true in his argument that the external, the nebulae which are seen are all external galaxies. What Hubble did is to he measured the distance to the galaxies, and using the Henry test method, and then he found that distance to be more than the expanse of our galaxy, and then he pointed out that all these most of these, not all, most of these nebulae are galaxies external to us. And also he measured something called a redshift, about which we will come to a little later. So let us just understand what is a galaxy. This is sort of a spiral galaxy. The Milky Way galaxy is a spiral galaxy. See, you can see all these patchy white spots over there. These are all stars, very dense packed stars over here. And this galaxy is very huge. This is taken a photographic plate, and it looked like very small, but it's actually very huge. All these white patches are where the new stars are there, new stars are there, and these red portions are there where there are old stars are there. So sun is a star, you know, and likewise there are 10 raised to 11 stars in our galaxy. This is not the picture of our galaxy. We are coming to that. So what is a galaxy? A galaxy is a huge gravitationally bound system of stars. Then gas is there in between, hydrogen and helium, and then dust from the explosion of other earlier stars is also there. Then dark matter is there, and at the extreme center there is something called the supermassive black hole. So this is the structure of a galaxy. Most of you might have seen the picture of our galaxy as well as the other galaxies and all. So this is just a galaxy. This I mentioned for those who are maybe not specialists in those who are not studied astronomy. So galaxies are a birthplace of stars, which are synthesizing all other elements heavier than hydrogen and helium in the universe. So whatever elements we have, even in our body, maybe our body may have some iron, some sulfur, etc. All these, and some carbon, etc. All these were synthesized within the stars. Then how it came into our bodies? When the sun was formed, sun and the earth was formed together, and earth later separated from the sun. So then sun and the earth formed together. Then it might have collected gas, hydrogen and helium gas from the surroundings in order to become the sun. So in the neighborhood of the sun, where sun formed, earlier there might have been the explosion of some other stars, which brought out whatever prepared by it in its interior, other elements like carbon, sulfur, etc. So all these the synthesized elements got into sun and into earth, and most probably into our body. So actually we are made of stardust, so to say. Now the other elements other than hydrogen and helium, which are there, if it is there in our body, all are coming from synthesis of these elements in some other star, which we even do not know which star, which exploded in the neighborhood of the sun very many years back. Okay, this is just some story which may require much more of time to tell about, but I am just cutting short. Now, the Milky Way galaxy, I have told you, Milky Way galaxy, we can see the Milky Way galaxy like a patch of light over here. All these individual stars are also part of Milky Way galaxy. This is the central portion of Milky Way galaxy, so to say. And Galileo understood that this central portion, even though it looks like a patch of some milk which is flown through this, poured through the sky, actually this is highly dense stars which are forming this portion of the Milky Way. And this is currently estimated to have approximately 200 billion stars. So what Herschel made is only a very few, tiny portion of this whole Milky Way galaxy. And we should also just tell about the scale of the universe, how we make measurements. So the distance between the sun and the earth is usually termed as 1 astronomical unit. And velocity of light, as many of you would know, is 3 lakh kilometers per second. Now, 1 astronomical unit is actually 93 million miles, and the light from the sun takes 8 minutes to reach us. So the distance between the sun and the earth is usually denoted as 8 light minutes. Even with this very large velocity, the light will take almost 8 minutes to reach us from the sun. So the sun is at 8 light minutes away. So light minute is a unit of distance, please remember. So 8 light minutes. So there are bigger units like this. 1 light year is a bigger unit, is the distance that light travels in 1 year in vacuum. Now the nearest star to our sun is the Proxima Centauri, which is almost like at a distance of 4.2 light years. Means the light which starts from the Proxima Centauri will reach us only after 4 years. So what we see now will be the shape or size of the, or whatever is there in the Proxima Centauri 4 years back. So this is a very interesting thing. If we are able to look at objects which are very far away, farther and farther away from us, then we will be seeing them in a much younger stage. So this is the way into, this is a method to peep into the origin of the universe. To look into the origin of the universe or observe the origin of the universe. We cannot go up to the origin of the universe, but nearer to the origin we can go, origin of the universe. We need to look at farther and farther objects which are fainter and fainter, and this can be possible through making bigger telescopes. So 1 light year is almost like this much kilometer large. In kilometers is a very large value, and this is this much of astronomical unit. And there is another unit called 1 parsec. 1 parsec is a 3.26 light years, and 1 kiloparsec. So 1 kiloparsec is 1000 parsecs. So the usual galaxies will be having a size almost like a 30 kiloparsec or so. I told you that the Milky Way has an expanse of 1 lakh light years. This is almost like 31 kiloparsecs. And there are units called megaparsecs and gigaparsecs. Okay. So this you should remember. 1 light year is a huge distance, and 1 parsec is also a very, very huge distance. So that brings us into the discussion of what Milky Way looking like. Milky Way is a sort of a spiral galaxy, and all these are stars. And as we have understood from this is the top view, this is the side view. We cannot view like this, but these are all artists made all these things. We cannot even photograph the Milky Way galaxy since we are a part of that. Maybe we can take the different photographs and join it together to form such images. So from here to here, it is 1 lakh light years, and there is a bulge and a halo kind of thing like this, and the sun is somewhere over here, not at the center. We mentioned it. Sun is at one of the spiral lamps over here. If we say it over here, sun is over here, not at the center of the galaxy, but somewhere here. So it contains roughly 2 into 10 raised to 11 stars. And the sun is at this arm, and all these things we have mentioned. And at the center, there is a supermassive black hole, which is called a Sagittarius A, which is having the mass of almost like a 10 raised to 6. That is 1 crore. 1 crore sun's mass, almost like that's that much of a big supermassive black hole is sitting at the center. Now this is our neighboring galaxy. This galaxy we have seen, Hubble had done his measurement using this galaxy. At that time this galaxy didn't look that spectacular, and ironically this is a picture or image taken using the Hubble Space Telescope, which is a telescope which came later in the name of Hubble. So this is the latest picture of the Andromeda galaxy. So Hubble did experiment, observe this galaxy for the first time to tell us that there are external galaxies. And this is the picture of that galaxy taken using a telescope named after Hubble many years after. So this is our neighbor Andromeda galaxy. It's the largest galaxy in our local group. This is from one end to another. It is 67 kiloparsec, and this galaxy is 2.5 million light years away. So that means the light from this galaxy will reach us only after 2.5 million. 1 million is 10 lakh. So 25 lakh years after. So what the light which we are seeing from Andromeda galaxy started from there 25 lakh years ago. So what we see Andromeda galaxy is like what it looked like 25 lakh years before. That is what we see now. Okay. Yeah, in 4.5 billion years, this may collide with our galaxy, and this is having 2.5 times the mass of the Milky Way and all these factors. Now we are coming into another aspect of Hubble. Hubble did measure the distances to the various nebulae, which he observed to be not nebulae but external galaxies. And then his assistant Milton Humanson and another scientist, Westos Riffer, they used this technique called spectral shift in order to understand whether these galaxies are at rest or they are moving. Then they found that these galaxies, which are earlier termed as a nebulae, were all rushing away from us. That is called the redshift. So this phenomena is called the redshift of spectral lines. Not that phenomena, but the corresponding change in the spectral observation is called the redshift. So this Hubble measured the distance to these galaxies and also the velocities of each galaxy. Different galaxies were having different velocities, and he found that there is a relationship between these two. And then there is a constant by name Hubble constant. And this Hubble constant, they propose that there is a constant by which these two are connected. And this Hubble constant is found to be 70 kilometer per second per megaparsec as its value nowadays. Earlier it was assumed to be somewhat 500, etc., which was a very inaccurate way of determining it. And this is called a Hubble law. And the Hubble law can be seen as a Hubble law is given by V is equal to h0d. This connects the velocity of galaxies with the distance of the galaxies. And all the galaxies are moving away from us, and the farther galaxies are moving faster away from us. And this relationship is plotted in a graph like this. Actually, this graph is a very important graph. This is a milestone. Cosmology, a subtopic of astronomy, studying the origin and evolution of the universe, is based on this. The symbol law is the cornerstone of all the cosmological developments that happened. Cosmology started almost from here. And the beginning of observational cosmology. I mentioned already to you that the cosmology is the study of origin and evolution of the universe. This can be studied in different modes. Theoretical way we can study, observational way like what the Hubble was doing, and then you can do the simulations in computers and study the cosmology or the study the universe. Okay, so now I'm coming into another aspect. This is also another major milestone, working back from the concept that the galaxies are moving away from us. That means the universe is expanding. The scientist and the Roman Catholic priest George Lemaitre, he proposed what became known as the Big Bang theory of the origin of universe. What he was telling is, if these galaxies are moving away and away, suppose we work back from here, like we are running a movie backwards, then we will see that all these galaxies coming closer, 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 and it will come together in a point. Then he postulated that might be all these galaxies, etc., might have formed from a point. So it's due to a large expansion from a point, and this theory is called the Big Bang theory of the origin of the universe. And this is George Lemaitre, and this is the artist's expression of how the George Lemaitre imagined that all these galaxies might have been come from a point. And in fact, this theory of a Big Bang theory was rebuked by the people at that time. And in order to ridicule him, they just coined the word Big Bang theory, but it stuck over there. And this is now the Big Bang theory is the theory with the strongest observational support. Okay. The common analogy explains that space itself is expanding, carrying galaxies with it, like raisins in a rising loaf of bread. When a bread is cooked, if you put raisins, raisins will move away. Like that, all the galaxies are moving away from us. This is something which I may not go into detail. This is about how from the beginning of the universe, all these atoms were formed, and then galaxies were formed, and how the universe starts looking like this. This will itself require somewhat like 5 minutes to explain. So let us just keep it over there and go to the next slides, because the time is fast running. So the major evidences in favor of Big Bang theory. So this Big Bang theory was, I told you, initially rebuked by the major scientists at that time, who believed in some other theory by name the steady state theory. But many evidences came in favor of a Big Bang theory, and now the Big Bang theory is the most accepted theory regarding the origin and evolution of the universe. One important theory was when scientists measured the content of hydrogen and helium in the universe, then hydrogen was found to be 75% of the universe and 25% is a helium. And this could be theoretically predicted if the universe had started in a Big Bang, then this need to be the proportion between helium and hydrogen. I am not going into the details, but this was experimentally seen that the universe contains 75% of observationally seen, not experimentally, 75% hydrogen and 25% helium, and that was also theoretically reached that by George Gamow. So the theoretical expectation was proved to be right observationally, and if this is like this, then the universe might have formed using through a Big Bang process. Now the expansion of the universe, which was seen by Edwin Hubble, is a real reason to believe that the universe might have been formed from a point. That was the way in which the Lemaitre also reached at the Big Bang theory. And then third one is, it was like scientists were thinking that if the universe expanded from a point, then in the beginning also there might have been radiation, light and other radiations might have been there. And this remnant of this radiation should exist everywhere in the universe. So ever the ever happening, or these radiations which are present all throughout the universe, which is called the cosmic microwave background radiation, was postulated theoretically by these scientists. And later on, this cosmic microwave background radiation was accidentally discovered in 1965. This prediction was in 1948, and people were not able to visualize it, observe it. But two scientists, Arno Penzias and Robert Wilson, they were trying to detect source of some radiation. They were doing something on some antennas, and there were some unwanted noise in the antenna, and that just they wanted to try to get rid of that noise. But however they tried, this background noise remained there, and then they just reported that, telling that we have this background noise in this antenna and all. And we can see that their data, however, showed a background noise from the microwave signal corresponding to a temperature of approximately 2.7 Kelvin, and appeared to be emitted from every direction. So this radio noise was coming from every direction. And actually they thought this as an aberration, but this is the cosmic microwave background radiation which are being sought by scientists in the nearby Princeton University. But they didn't knew that they were looking for this. And there is radiation from the earliest observable moment of the evolution of the universe. What they are seeing serendipitously is the radiation from the earliest observable moment in the evolution of the universe, which is the cosmic microwave background radiation. Actually, those who discovered didn't know. And they didn't know that they have found their remnant radiation until the Princeton theorists told them. Princeton theorists were looking for this actually. But they walked away with the Nobel Prize in 1978. നമ്മുടെ മലയാളത്തിൽ പറയാമെങ്കിൽ മണ്ണും ചാരി ഒന്നും പെണ്ണും കൊണ്ട് പോയി എന്ന് പറഞ്ഞാല് ഇത് നോക്കിയിരുന്ന ആൾക്കല്ല കിട്ടിയത്, ഇത് കിട്ടിയത് ആക്സിഡന്റലായിട്ട് കണ്ടുപിടിച്ചവർക്ക്. കാരണം അവരാണ് ഒറിജിനലി അത് കണ്ടുപിടിച്ചത്, അതുകൊണ്ടാണ്. ഓക്കെ, സോ ദിസ് കോസ്മിക് മൈക്രോവേവ് ബാക്ക്ഗ്രൗണ്ട് റേഡിയേഷൻ is a very important nowadays, even though these two scientists, these are Arno Penzias and Robert Wilson, with their telescope, iconic telescope. I just wanted to show you this instrument, which is responsible for discovering this cosmic microwave background radiation, which proved to be a strong proof for the Big Bang theory, Big Bang hypothesis. So this is even though earlier it was thought that the radiation coming from every part of the sky was of the same intensity. Later on, not these two people, but later on, using telescopes and all, scientists found that there are a little mild variations in the amount of radiation coming from various directions. Even though it was observed to be same, it was expected to be the same. So these mild radiations are now postulated to be because of a very minor kind of density variations in the beginning of the universe. And these very minor density variations, some points contained a little more of matter. Then according to Newtonian law, wherever there is more matter, more the neighboring matter will be attracted towards that matter because of Newton's law. And then the matter got clubbed together in order to form all these structures like the galaxies, stars, etc. So this theory holds very likely to be good. And the structure formation evidences are actually coming from this anisotropy in the cosmic microwave background radiation. Even though this whole sky was expected to be giving out the same amount of same intensity of radiation, there were a little lesser intensity here, more intensity there, and like that. So this indicated the anisotropies in cosmic microwave background radiation, and this could explain how all the structures in the universe did happen. So like that way, this CMBR discovery is a very great milestone in understanding the universe. Now we go into another milestone. And this milestone is connected with the advent of multi-wavelength astronomy. Earlier, I have mentioned to you about all these telescopes. These are all optical telescopes. Through these telescopes, we can see the visible light. Those light which we can see through our eyes can be seen through these telescopes also. But there are also other wavelengths which is not visible to the eye. For example, the radiations which are coming to our telephones, our cell phones, they are all radio radiations. the television, radio, everything works with the radiations coming which are unseen to us, and also the X-ray, which we usually encounter when we are going to the hospital. The X-ray radiations are also not seen by our eyes. So most objects in the universe radiate at wavelengths that our eyes cannot see. Astronomers use telescopes with detection devices that are sensitive to wavelengths other than visible light. Different wavelengths reveal various physical properties like temperature, color, composition, dynamical status, etc. Of the object. So this multi-wavelength astronomy was another milestone. So let us go into the details. So this is electromagnetic spectrum. So electromagnetic spectrum gives us the details of what all radiations are, electromagnetic radiations are there: gamma rays, X-rays, UV, IR, microwave, radio waves, etc. This is the part of the spectrum which we can see by our eye. All other we cannot see. But the objects are also emitting radiation which we cannot see. But one problem is all this light cannot come through to the surface of the earth because of the atmosphere. Atmosphere absorbs much of the electromagnetic radiations. Only visible light and radio waves can penetrate and reach the bottom, the surface of earth. So this is opacity given as this is the various wavelengths. So only this wavelength as well as this wavelength is observable on the surface of the earth. So what will we do to observe other wavelengths? Then we need to send probes to the exterior of our atmosphere. So that happened in the era of space telescopes. So later on, when the satellite technology got matured, people were able to send satellites to the to space, and these satellites also worked as telescopes, and they provided multi-wavelength data to the astronomy community. So there are various telescopes in the form of satellites which are revolving around the earth outside the atmosphere, and they are capable of catching the invisible radiations and also those radiations like X-rays, etc., which are being blocked by the atmosphere. So then we could see the universe in a better shape. So these space telescopes are instruments which made it possible to perceive the objects in the universe in a better way. So this, I just have a one cartoon here wherein we have just pictured this I took from some particular site, and all these are satellites. These are all in various wavelengths. Now the wavelengths are given here: gamma ray, X-ray, ultraviolet, visible, infrared, microwave, radio. So radio, these are in each wavelength we have a different satellites in the sky. This is Earth, and these are the biggest telescopes which are there on the surface of the Earth. The Keck telescope is a 10-meter telescope. This is an 8-meter. This is also 10-meter, and there are these radio dishes also here. So this is a picture which characterizes all the important kind of ground-based and the space-based telescopes. All these space-based telescopes are instrumental in making the understanding of the universe in a better way. So this is just a galaxy which is seen using radio, X-ray, and optical. If you see the optical galaxy, it will be only somewhere here. A small portion it will occupy. So if you look at X-ray, then this is the X-ray image which is surrounding the galaxy. And if you look at radio, then in radio, this galaxy will shine like this. So this is actually coming from radio. This X-ray is also connected with the this is actually coming from the galaxy. The original optical galaxy, which we can see using an optical telescope, will be only this much. So all this could be seen only if we have a radio as well as X-ray observations. These are all processes which are happening from the center of the galaxy. So in order to understand whatever objects which are there in the universe properly, we require different wavelength observations. So this is a portion where seen as a this invisible light, this is a dark patch, but when we look it through an infrared telescope, this dark patch is filled with objects. So here there is some absorbing feature by which the optical light is absorbed. So but infrared light is not absorbed. So we can see this in a better light if we are looking it through infrared telescopes. This is just the image of our Milky Way galaxy if we are looking at with various wavelengths. So just to show you, that's all. This all looks different, but this is the image of the same Milky Way galaxy taken in different wavelengths. So only unless and until we are able to take the measurements, observations using different wavelengths, we are not able to picturize the universe in a accurate condition and in a real condition. So this is another galaxy which is seen in X-ray and UV. This looks a little different. And the same galaxy looked in radio. In radio, it is entirely different. This is in infrared. That also looks different. So the thing is, situation before the advent of this multi-wavelength astronomy is that the universe or the objects in the universe was looked at like the parable of a blind man and the elephant. So the blind man, you know the story. I'm not explaining this story. So through optical telescope, we were only seeing a very small portion of the whole the universe. So the perception of the universe actually got enhanced when we could use all these space satellites or space telescopes so that we understand the objects in a better way. Okay. Now we come into one among these space telescopes, which is very famous, which is called the Hubble Space Telescope. I already told you that there is a telescope by the name of Edwin Hubble. And this was launched in the 24th of April 1990. If you work the years together, then we understand that this is the 30th year of this telescope. This telescope was designed only for 15 years, and now it is a 30th year. And this has got a mirror which is 2.4 meter. And this revolves around the Earth in 97 minutes. It completes one revolution, and all these details are there. One of the major kind of achievements through the observation by this Hubble is that now we know that the age of the universe is between 13 to 14 billion years. This has become possible because of this telescope. And also there are something like 10,000 scientific articles which are being published in the with the images as well as spectra obtained from Hubble Space Telescope. There is a very interesting story with regard to the Hubble Space Telescope. Hubble Space Telescope, you know that you can see that I am putting this spectacle. This is because I cannot see. So I needed a glass for enhancing my sight. Likewise, when the Hubble's telescope was launched, it had some problem with its mirror, and it was not the images were not clear. And later on, scientists could travel to the Hubble Space Telescope by space shuttle, and they replayed something, and then Hubble was working very properly. So these are called service missions. So this practice of going to Hubble and taking away some of his instruments and putting new instruments continued. And this is called service missions. So all these details are there in the Hubble site, and you can go and get these very interesting videos are also there, how these instruments are being picked up by the astronauts, and new instruments are being placed there. It is not so easy to do like in the surface of the Earth. So you may look into that ideas. So time is running out fast, so I am a little behind schedule. I'll be going a little faster. So many of this Hubble Space Telescope could bring in lot of new ideas. One idea is that we can peep deeper into the universe. So we can peep deeper into the universe. So those are called Hubble Deep Fields. Hubble Deep Field gives a treasure of information to us. So we can observe a portion of the sky for a very long interval of time using the Hubble telescope. And then these are the images obtained through such a ultra deep. This is ultra deep field, and this is deep field. So most of these galaxies which we see here are very far away galaxies which are observed by the Hubble. So the very far away galaxies, as I might have told you, indicates, or it actually indicates the younger period of evolution of the universe. So like these deep fields are capable of giving us an idea about what was the universe like in the beginning, or the beginning stages. Okay, so I mentioned to you about the Hubble constant. These Hubble, ironically, this Hubble Space Telescope, one of the intentions of this Hubble Space Telescope was to make an accurate determination of Hubble constant. Now, then I mentioned to you regarding the black holes at the center of galaxies. Many great ideas regarding these black holes at the center of the galaxies came through the observation by this space telescope, the Hubble Space Telescope. So this Hubble Space Telescope is so special that it actually changed the whole scenario of astronomy and astrophysics. So that's why I'm putting it among the milestones in the development. And the Hubble Space Telescope is also an instrument. So this instrument which brought out all these very important discoveries or about the universe, or in other words, we could perceive the universe in a better light using this instrument, the Hubble Space Telescope. This is the study of intergalactic medium. I'm not explaining this. You can see there is a dip over here. So from this dip in the light received from the intergalactic medium, people could study the components of the intergalactic medium. And this is exoplanets. Hopefully you will know that other than the planets which are there in the solar system, scientists were able to find out somewhat like 4,000 planets which are revolving around the stars other than the sun. So those are called exoplanets. So in order to study the exoplanet, so this is another star, and if the exoplanet is here, and when the light from the star passes through this atmosphere, this light can be deciphered by this, this Hubble can analyze this light and find out what is the composition of the atmosphere. If the composition of the atmosphere indicates methane, then obviously there would be the possibility of life which is there in the surface of the planet. It might be like Earth. So this kind of spectroscopic analysis of the atmospheric structure is being done by the Hubble Space Telescope. Now, I mentioned to you about the star-forming regions in our galaxy. So these are two such regions, Pillars of Creation and Horsehead Nebula, and the studies were done by the Hubble Space Telescope. Now, these are spectacular images from Hubble Space Telescope. These are like in galaxies which are interacting with each other, collision of galaxies. This is regarding planetary nebulae, the end stage of a star, the various kinds of stars ending in different ways. This is the explosion of a star. This is a planetary nebulae forming. The outer portions of the stars are expanding to form this planetary nebulae, and the central portions of the star, when the star has died out, will become either of the three things, either of the three final compact objects. One is the white dwarf, second is the neutron star, or the black hole. I'm mentioning this because we are yet to tell about that. Okay. Now this is another idea, gravitational lensing. If you have a very far away object, then if there is a galaxy cluster in front, then we can get the mass of this galaxy cluster by looking at the light which is coming from the far away object. This is called the gravitational lensing. It is like the lenses for focus light. The galaxies can focus the light coming from a very far away object. Now these are all results. Many of these results we have already discussed. These are the results which came from Hubble. And Hubble has completed 30 years now. And another important satellite, the only satellite telescope which India is having, is the AstroSat, which is a multi-wavelength telescope. And this is the structure of the AstroSat. This was launched some 3-4 years back. And this is the latest discovery made by Professor Kanak Saha from Ayuka, Pune in last month. This is about AstroSat detecting a faraway galaxy emitting ultraviolet light. This was discovered by Kanak Saha using the AstroSat. Now we are going into, actually our time is almost over, and we are going into just another window, that is gravitational waves. I will make it very quick. So you know that you know about Einstein. Einstein made a very important milestone is his two theories, special theory of relativity and the general theory of relativity. And the general theory came in 1916. And I'm not the important aspect of the general theory of relativity is that the general theory of relativity describes gravity as the geometric property of space and time, or space-time. So the gravity is actually an entity which is connected with the geometry of the space-time. So the space and time is we know space and we know time. Space and time is taken as a single entity. And actually, if a massive body is being placed at some place in the space, then it creates a curvature in space-time. So this curvature is actually responsible for the gravity. That is the main idea of the general theory of gravity. Now I am just going a little faster. Please excuse me for that. This is some equation which is called Einstein's field equations. This is a very important equation. This equation is a very efficient way in which the universe as a whole can be mathematically represented into an equation. If the universe is can be mathematically represented into an equation, then we can put these equations into some computer or so and see how the universe is evolving. So this thing is happening in the case of astrophysical simulations. You see in the left, you cannot even distinguish between these two images. In the left from here, we have the real observations made on a portion of the sky. And in the right, this is the simulations, the result of simulations from a computer. By putting in the initial conditions, computer has synthesized how the sky will look like. And this is exactly almost similar. So computers can be utilized for understanding how the universe looks like or how it evolves. So this is a new method, or not new, but very, very recent method of understanding the universe by using the computers. So the computer is an instrument, as you know. So computer is well utilized for synthesizing the images of the universe, and it looks almost like the original images which we get through the telescopes. Now I'm coming into the last topic which we will discuss. Last milestone. It's not the last, so to say, but one of the milestones, but which is a very recent milestone, which is the detection of the gravitational waves, which was predicted by Einstein in 1918 and 1916. So the first detection of gravitational waves were happening in 2015 and 16. 100 years after Einstein did predict that there will be gravitational waves coming from objects in the sky. So the space-time, we talked about the space-time. So if there are two, I also talked to you about the black holes, neutron stars, etc. Two black holes, which are the very compact form of final stage of stars, they can come and collide with each other, which will be a very energetic phenomena, and there will be waves in space-time. This space-time, if you can assume it like a surface of a pond, then this will happen. This will result in the waves which are happening there in the space-time, and that is called a gravitational wave. So this was predicted 100 years before, and I'm skipping this. If you could detect gravitational waves, an entirely new spectrum in which spectrum by which we can explore the universe. So this is what was expected by scientists, and they were trying for almost like 30 years to build up an instrument in order to detect gravitational waves, and they succeeded in 2015. So what all are gravitational wave sources? If two black holes come closer by inspiraling and come closer, and they collide each other, then intense gravitational waves may come through. See, they are coming closer, colliding with each other, forming one entity. And the typical sources are binary black holes, two black holes, or binary neutron stars, two neutron stars, or binary white dwarfs. I mentioned to you that stars will end up either as a white dwarf, or a neutron star, or a black hole. Or if this comes to and collides with each other, then we will have these gravitational waves. Now, electromagnetic waves, which we saw earlier, is different from gravitational. Gravitational waves are actually ripples in space-time. Electromagnetic waves are some radiations which are traveling through space-time. And the typical frequency of electromagnetic waves is from 10 raised to 4 hertz to 10 raised to 20 hertz. Whereas for the gravitational waves, the typical frequency is this much. So these are two different entities, but the common thing is that both of them are traveling with the same speed, that is the speed of light. Okay, so this is the GW spectrum, means the different, we saw the electromagnetic spectrum earlier, like that, which all frequencies are possible. I'm not going into the details. This is the electromagnetic spectrum, which we already saw. Now, the importance of gravitational waves. These gravitational waves are very important to test whether the speed of light, whether they travel with the speed of light, and to study about the gravitons, to study the black holes, etc. So this is very important to detect gravitational waves. So the gravitational waves are detected by laser interferometers. Laser interferometers are splitting the light. Maybe I can give it in a video. So these are two LIGO observatories, laser interferometer gravitational wave detectors. These two detectors were responsible for the first ever detection of the gravitational waves, and these two detectors are in America, and they are away 3002 kilometers. But the observation of gravitational waves here as well as here were consolidated together to announce the first detection of gravitational waves. So this is a LIGO Hanford, and this is a LIGO Livingston. So two detectors. If there are more detectors, then these gravitational waves can be detected easily. But even with these two detectors, they could detect the first gravitational wave. Gravitational waves are always there, which passes through the Earth due to the collision of black holes, which are happening very far away. But till now, till 2015, the instruments were not sufficient for detecting them. The instruments become sufficient in 2015, and they could detect the waves.
In an interferometer, a laser beam is split into
just
two
listen
beams.
to this.
Mirrors reflect the beams, so they meet again at a starting point. If now the distance to each mirror is exactly the same, no light will be seen by the detector. The waves of one beam extinguish those of the other beam. This is called interference. A passing gravitational wave distorts space, making one arm slightly shorter and the other arm a little longer. The light waves do not cancel each other anymore, and we now measure a tiny signal in the detector.
Okay, so you might have understood that it should have two arms like this. And these arms in the case of LIGO is 4 kilometers. If the length of the arm is very larger, then the detection efficiency is high. So there will be a large tunnel of 4 kilometers running in this direction, another in this direction, and the lasers will be passing through this. And there will be mirrors reflecting them. And when gravitational wave comes, these mirrors will be deflected by somewhat like 10 raised to minus 20 meter, which is very small. And that reflection actually produces some effect from which we can detect the gravitational wave. So this is a one arm which is 4 kilometer, a large tunnel. This is another tunnel, 4 kilometer. And a laser is running from here to here through this mirror and getting reflected. And when the gravitational wave comes, there are differences which can be detected. And next one, I am not going into that because that is the same as the above. And this is the first ever gravitational wave signal observed. Just just view this. This is the signal which is obtained from Hanford. This is from Livingston. This is the two signals put together. And then they could identify this kind of unexpected wave from two black holes colliding. And how they understood that? See, these are the black holes, and these black holes are inspiraling. They're coming closer and closer together like this, and they are meeting. So when they are inspiraling like this, the wave should look like this. Scientists know this. And when they are closer, it will come closer. And when they are colliding, it will just enhance its intensity, and then it will die down when it comes together. So this was observed as the signal. So they understood that these two black holes are coming and colliding each other, so that this particular signal is produced. Now, just listen to this. These are the signals which are observed. This sound is not heard at that time, but the frequency is almost like a sound speed, but the intensity, since it is very low, we can't hear this sound. But when this sound can be enhanced like this will be equivalent to somewhat a sound like this. So scientists could find that the collision did happen between two black holes which are of 36 times the mass of the sun and 29 times the mass of the sun. This is a very new discovery, and the final black hole was having 62 times the mass of the sun. And the energy radiated is almost like equal to 3 times the mass of the sun. Huge amount of energy was radiated. And the importance of this first discovery is that this is the first ever direct detection of gravitational waves from merging binary black holes, two black holes coming together. Even the black holes were not observed till then, but this is a detection of a black hole itself. And then black hole pairs were detected for the first time. So this is the most luminous event which was observed by scientists until then. Now, I just cannot resist to show you this slide. This slide gives the idea that there were 60 scientists in the LIGO consortium, which did take place in the discovery, first detection of gravitational waves. There were 1,000 scientists all throughout the world, and out of that, 60 scientists were Indian scientists. And out of this, these are the people from Kerala. Since the talk is happening in Kerala, I just I should flash this. See, these people are very young people who are from Kerala. This is maybe the youngest one. He is from Tichur, and he is now in Germany. And all these people are in various institutes in India, and they are all part of the first detection of gravitational waves. This is something, a proud moment, proud matter for all us in Kerala. Okay, so there were further detections. I'm not going into the details. This was the first detection which actually happened in 14th of September 2015. So this GW, which came and detected by the LIGO, is termed as a 14th September 15. So 150914. That is the way in which it is nomenclature. Okay. So there were other further detections also of these are the dates or etc. which are given. You can get all these details from the LIGO website. Okay. So now I just want to mention to you about a another GW 170817, which happened on 17th of August 2017. This is called the kilonova. Other than the two black holes coming together, actually there were the first instance where two neutron stars were coming together and colliding. So you can see the waveforms in the case of black hole collisions like this, but this neutron hole collision took almost, it existed almost for 100 seconds, almost for 100 seconds. This is the signal which was observed when it is converted into equivalent sound signal. You can see that this signal is existing for more time, for almost like 100 seconds. So I'm sorry for the surpassing the time. Maybe I'll finish very soon. I'm extremely sorry for that. Okay. So this electromagnetic, the particular thing about this GW 170817 is that together with the gravitational waves, the scientists were able to also get electromagnetic radiations from the source, and also they were able to pinpoint where the source is. And for that, the Hubble Space Telescope was also used. So the GW 170917 is termed as the dawn of a multi-messenger astronomy. Multi-messenger means we can use electromagnetic waves. We can also use gravitational waves to pinpoint the object and to study about that particular object and the collision which is happening there, the neutron star collision. So this is something very interesting. See, you can see here, scientists could detect that there were a lot of platinum, gold, and silver formed due to this collision of two neutron stars. So 50 Earth masses worth of silver and 100 Earth masses of gold. 100 times the mass of the Earth gold was created in that collision event. So this is probably a perfect place to smuggle gold from. We are all hearing news about the smuggling of gold and the people doing that from in certain disguise, and some people are in jail. We hear about all these news. Maybe though, if those people could travel to these faraway distances, then they could have got this much of gold from there. But unfortunately, it is not possible. Okay. So this is the various waveforms again depicted of the various gravitational waves detected. And this is the last one, the two binary black holes colliding. Sorry, binary neutron stars colliding. These are all from two black holes which are colliding. And this is from the neutron star which is colliding. And these are the different detections of gravitational waves. This here there is mass. So these two masses, solar mass, they joining together to form this. They are forming this. This all resulted in gravitational wave detections. And this is the latest one, which happened last month, which was pronounced last month, wherein an almost 80 solar mass black hole is colliding with another 80 solar mass black hole to form a 160 solar mass black hole. This 160 solar mass black hole is according to our scientific conventions, this cannot be forming out of stars. So these are called intermediate black holes. These were just a theory till now, but scientists have just detected this through the study of gravitational waves. For this study, together with LIGO, the Virgo detector in Italy was also taking part in this discovery, which happened just last month. Now this is just another cartoon which shows how all the gravitational wave detections did happen from various mass black holes. And this is the last one, the intermediate mass black hole, which happened in, see, look at this date, 19/05/21. So 21st of May 2019. But it was declared only last month. This scientists take a little time, on almost a year, to decipher the signals and to pronounce that it is a real gravitational wave. Now our country is also coming into the league of the gravitational wave detectors. We are building up a gravitational wave detector in Maharashtra, and this will enhance the detection efficiency. That is the reason why the Indian LIGO detector is going to be important. Now finally, this is almost my final slide. So the universe, what we know and what we do not know. I didn't mention about this exactly, but I am just stopping this by telling that what we know about now is the ordinary matter which we see in galaxies, etc., are only 4.9% of the whole universe. We scientists now understand that there is something called the dark matter, which forms almost 26.8%, which we do not know much about, and there is the dark energy, which is present almost 68.3% of the universe. So the 68.3% of the universe is composed of dark energy, 26.8% dark matter, and only 5% ordinary matter. What we know till now is only about this 5% ordinary matter. So we don't even know much. So this data is from the Planck satellite. That's why I kept it. So much is being perceived about the universe, but much more remain. So this is the take-home message which I just wanted to tell you. Thank you. And also just using a few seconds, I would like to dedicate my talk to the everlasting memory of Professor Govind Swarup. He passed away last Monday. This was a sad news for all of us who are working in radio astronomy. This is the Professor Govind Swarup is an iconic figure. He built this GMRT, Giant Microwave Radio Telescope, which is a world-renowned telescope. And this is a telescope used for by radio astronomers. I am actually doing many of my research using this GMRT. So he is a most revered scientist who just passed away, and he built this giant microwave radio telescope. And if if the organizers allow, I would like to give another talk later in this series about this. Thank you. This is the end of the presentation, and I would like to thank my friend Vivek and my colleague Sudesh Tangapan for helping me in some. So Vivek has given me, shared some of his slides, and Sudesh was helping me in making all this PPT. And with a profound apologies, I would like to stop here. I might have taken almost like 1 hour 15 minutes. So sorry about that. Thank you.
Thank you, Dr. Joe Jacob, for your brilliant exposition, a very scholarly presentation, highly inspiring. And I'm sure those who attended the talk would be finding a source of inspiration and a lot of indicate areas of indication for their future research, even current research. I really appreciate on behalf of LIPI and the principal advisor, Dr. K. Babu Joseph, and the Loyola Institute. We extend our very sincere gratitude to Professor Dr. Joe Jacob. You have really unraveled the mysteries of the universe in no time. Billions of aged universe, I mean, and the different stages in the development of astronomy, the different milestones in the historical trajectory of astronomy, all these were highlighted very beautifully and comprehensively. It was, even for an amateur astronomer or even for a person who is just interested in those things, really digestible. And I appreciate it. Now it's the question hour. Dear friends, all of you are welcome to join this discussion. The floor is open for discussion. I request the participants either message your questions or ask in person, ask directly to Dr. Joe Jacob, and let's have some fruitful time in discussion.
Thank you, Father. Sorry for exceeding the time.
Actually, as I said, I didn't feel I was very keen attending this. Likewise, I feel others also would be feeling the same. Let's listen to their questions. Thank you, Dr. George.
Sir, I have one question.
Yes, please.
Sir, your talk was very inspiring and it was highly informative. And according to the Big Bang theory, universe might have originated from a single point and it is still expanding. So if it expands like this, what will happen to the universe in the future, or what will be the ultimate fate of the universe, or what is Big Rip scenario?
Yeah, that's a very nice question. Actually, I had a few slides which I included in the presentation earlier. But since I had to limit this talk even to almost like 1 hour, I had to remove all those slides. So I have mentioned to you regarding the Einstein's equations. From Einstein's equations, scientists by Friedman and also the scientist Le Maitre, they developed, they actually solved those equations, and they brought out some results by which they could predict 3 different stages for the end of the universe. 3 possible stages of end of the universe. One is, since the universe is expanding, it can just go ahead expanding, and maybe it can go ahead with expanding with the uniform speed. In that case, the universe will go on expanding, and all these galaxies will move away from each other, and it will be like all will be going far away from each other, and it's sort of called the all will deteriorate or all will move away from each other. And another scenario is like if the universe is expanding and if it is slowing down, then after some time, maybe all the galaxies may stop expanding, and then it may come back after stoppage of expansion. It may come back and again a crunch will take place, and this may repeat itself. A big bang, then all crunching to a single point, and then another big bang, then another crunching, like kind of this is called a cyclic universe, the theory of cyclic universe. And also another scenario can happen wherein the universe its expansion can be with a little acceleration, or its velocity of expansion may increase, and it will just go on this is called a big rip. This is called a big rip. Big crunch is there, big rip is there, and the cyclic universe thing is there. So in big rip, all these galaxies will move away from each other, and even in the galaxies, the stars will move away from each other, and all will be dispersed, kind of thing. So these are all imaginations, or maybe in mathematical terms, we can think about all these things. And which will be the final stage will depend upon the very accurate measurements about the composition of the universe, particularly the dark energy, which I didn't mention a word at all. Is very important in finally deciding what will happen. Now, as I have heard from cosmologists, the current belief is that the universe will expand forever. This I'm not sure about, because I'm not a specialist in this initial cosmology, or sorry, the cosmology where we are talking about the end of the universe. But I have heard from somebody telling some talk that the universe is expected, as far as the data which we have at our hand, it will be just going on expanding forever. So these are the three different possibilities. So these three possibilities can be derived out of the equation, the Einstein's field equation. See the importance of Einstein's field equations. And Einstein's field equations are always very helpful when we are dealing with these black holes where the gravity is very high. In other cases, we may require only the Newtonian gravity, but wherever these exotic conditions of a very high gravity is there, then these Einstein's equations are used.
Thank you, sir.
Did I answer your question?
Yes, sir. Thank you so much.
Okay.
And I see a question in the message. We know nothing about dark matter or dark energy. How exactly did we come to know the idea of the existence of the dark matter? Those are anything to be commented.
Okay. Yeah, that is also a very nice question. Very nice question. Maybe if time is there, I have some slides in my appendix. Actually, that was a part of this talk, but when I made it concise, then I did.
Okay.
Yeah, this is the role of dark matter. See, this is how this is the evidence for dark matter. This lady scientist was she's a very famous woman astronomer by name Vera Rubin. She gave in the first direct evidence of dark matter. So that was given. So she was there till 2016. She died on December 25th, 2016. So if you are making a graph of a distance, this is the case of a galaxy. See, here there is a galaxy, and from the center, if you go out like this at 5 kiloparsec, 10 kiloparsec, etc., then we measure the rotational velocity of this galaxy. So most of the galaxies are in rotation. So if you measure the rotational velocities, so if you are taking only this kind of luminous disk means this optical from where the optical light is coming from, and we use that mass only for calculating the velocities, then we will get a velocity graph like this. It should be like this. But when scientists originally did the experiments and they observed, then the graph was going like this. See, we are not having much matter over there. That is our expectation, since we don't see any luminosity over there. But actually, towards the outskirts of the galaxy, we have a more dark matter than the inner side. That is the reason why, since there is matter over here, but they are invisible. So this is because of this matter that the that the rotational velocity remains the same, or almost the same, not exactly the same. It goes like this because of the presence of dark matter. So this was proved beyond doubt by drawing this rotation curve of a galaxy by Vera Rubin. And also in galaxies, this Fritz-Zwicky, he postulated about dark matter as the say dark matter is class. Sorry, these are all other details of that. Dark matter in between galaxies also was postulated by Fritz-Zwicky. And there is this postulate that all these galaxies, etc., are for. I'm putting this slide over here so that you can read. All these dark matter, all these galaxies which we see, actually formed when there were initially dark matter clumps which were formed, dark matter consolidations which were formed, and all this baryonic matter. Baryonic matter means the matter which we can see or we can perceive. Those matter all fell into sort of that dark matter so as to form the galaxy. So this theory is there. So dark matter potential well theory, so you can say that there are potential wells which are formed by the dark matter, and the baryonic matter fell into this dark matter potential so as to consolidate itself into a sort of a galaxy and all. So the structure formation is actually theoretized in connection with the dark matter. And also from the various measurements on this proof of dark matter can be heard from the measurements of cosmic microwave background radiation. And I have shown you a satellite which is here, this Planck satellite. So all these measurements a Planck satellite is launched to study the cosmic microwave background radiation. So from the cosmic microwave background radiation also we get a perfect idea about how much is dark energy, how much is dark matter, and how much is ordinary matter. I'm not able to explain the details of that. So for the cosmic microwave background radiation, there are a few peaks, and the peaks are an indication of the composition in some way. So there should be some calculations done out of that. So I'm not sure, I'm almost sure that I didn't answer, might not have answered it properly, but I have given you some hints regarding how the evidence, if the question is what is the evidence, then I have answered the question. Okay, thank you.
Anyway, I have a question that's out of curiosity, Joe sir.
Welcome, welcome.
You know, Dr. Joe, you are engaged in the teamwork. I mean, member of the team that discovered a supercluster galaxy Saraswati. And
Yes.
do you team up these days, or what's your current project or a future project? Just out of curiosity.
Yeah, currently we are involved in, you see, you mentioned about this Saraswati supercluster. In fact, I should see whether I have a picture of that. Maybe in another presentation I may have. I didn't put this into this presentation for want of time, because that is one among the discovery of a supercluster, which for more important things needed to be here. So this supercluster is a cluster of clusters. So cluster of galaxies, I mentioned to you about galaxy, and our own galaxy, Milky Way, is a part of a cluster of galaxies where there are 54 galaxies close by. And then there can be cluster of clusters. And these cluster of clusters or the superclusters are the biggest structures which are existing in the universe. And there are only a few of them known today, almost like less than 10. And our team could discover one such a supercluster, which is very far away, and which is named as Saraswati. And currently, what we are engaged in is to that is a portion of the sky which has got almost like 43 galaxy clusters which are detected. There are also undetected galaxy clusters in it. And actually, we are studying, making radio studies of that. The radio sources among these galaxies, those galaxies which are emitting radio, are being studied using GMRT. I mentioned to you about GMRT, which was built by Professor Govind Swarup, which is in Pune, which is one of the biggest galaxies which are existing. So, I'm sorry, which is one of the biggest telescopes which are existing in the particular wavelength. So currently we are studying the objects in the Saraswati supercluster using the GMRT, and trying to figure out what all sources are there and what would be the difference in the structure or morphology of these radio galaxies when they are in a sparse field, or when they are in a galaxy cluster, or if they are in the usual field of in the interstellar, if it is not connected with any galaxy, there are certain galaxies which are field galaxies, which are not connected with any galaxies, which are lonely. So such galaxies also can be radio galaxies. So what will be the radio emissions for such galaxies? What will be the radio emissions in the case of galaxies which are a member of galaxy clusters, etc. So this comparison study about the radio sources in the Saraswati supercluster area, that is what is the subject matter of our study currently. It will take so much of time because many hours of observation are required for that. For GMRT. GMRT is a satellite where many people want to take observations. So we will get only a part of the time, very small amount of time, maybe a few hours, maybe some 50 hour or 100 hour. So we may require so many such 100-hour periods to cover the whole Saraswati supercluster area. So we'll have to wait for 3 or 4 years to get the whole data. So this is the current project, Father.
Oh, thank you. And I see another question from Rajesh. Could you explain the origin of low mass elements like hydrogen and helium in the universe? And one more question, maybe you can just reserve it. John Isaac, sir, human life is possible only in Earth because of sunlight. Photosynthesis is carried out through sunlight. If the hydrogen present in the sun gets burned out completely, what will be the result? Is this the end, or we will have any alternative life in future? Too interesting.
These are very two interesting questions, which I can talk about it for like half an hour, but I can give you a concise answer. And the first question is about the composition of hydrogen and helium. See, I'm not able to tell you the detail, but two ways in which it can be found out. And you might have heard that the Nobel Prize being given to Jim Peebles last year, and he is working in physical cosmology. And gamma over alpha, etc., are the scientists, if I remember correctly, who might for the I'm not sure whether I'm right, but they worked out the proportion. It was there in the slide somewhere. Okay, it's a gamma is involved anyway, I think. So then they could, if the universe came through Big Bang, then there are certain conditions. It had a temperature. We can calculate how much temperature the initial point of expansion had after say 5 minutes or after 3 seconds. So people know about the evolution of the universe from 10 raised to minus 43 seconds after the Big Bang till now. That can be decipherated, and everything is not known. But from 3,70,000 years, this 3,70,000 years is has a special significance in the evolution history of the universe. From 3,70,000, it is the cosmic microwave background radiation emanated when the universe was 3,70,000 years old. So the reasons I am not going into, but the cosmic microwave background radiation was starting from there. Till then, the matter and the radiation was having so much of interaction, but from there onwards, the radiation was free. It was not that much interacting. So it carried all the characteristics from there. So in the beginning, scientists can calculate if the Big Bang, it was through the Big Bang that the universe formed. Then the initial conditions, they can think whether the initial conditions were sufficient for synthesis of which all elements. And they have found that it is like 25% should be helium and 75% approximately should be hydrogen, and there will be also traces of beryllium, etc., lower mass elements. So the universe is expanding and it's fast cooling, and its conditions cannot remain there for the formation of heavier elements. So this is some sort of an explanation which I can give you. And I have mentioned to you that later on, through observations, scientists are able to look up how much is the proportion, and they did get the same which was observed through the theory, and this formed one of the major evidence in favor of a Big Bang theory. So this is the answer which I can give you at this point. I may not be able to give you the details of how this was worked out. It's just got some calculations also. It's not that complex. You can get this calculation from internet if you are interested. If you just click the proportion of hydrogen and helium, the calculation in the beginning of the universe and calculation, you can get it from there. My second question is regarding the human life. This is a very discussed question, whether the human beings are there on the surface of Earth only. Now, I mentioned to you in passing that about exoplanets, that there are 4,000 exoplanets which are being discovered by the scientists till now. Almost 4,000 of them. These are all planets which are surrounding or which are going around the other stars. These stars are nearby to our sun, because the faraway stars, planets are not yet discovered because our instruments are not capable enough. So more exoplanets will be discovered when a 6-meter James Webb telescope will go into sky. This is the successor of the Hubble Space Telescope. Hubble Space Telescope is having a mirror of 2.5 meter diameter, but the James Webb Telescope will have a 6-meter mirror in it, and this will be launched by NASA in the coming years. And then more exoplanets will be discovered. And I mentioned to you regarding the idea that people are able to study the atmosphere of an exoplanet. I just mentioned using the Hubble Space Telescope, there it is possible to study the atmosphere of an exoplanet. This atmosphere contains methane. Methane is usually coming out of organic form. So the methane should be the result of life forms which are living there. Maybe the life process, when the life forms are decaying, methane will be formed, or the excreta of life forms maybe contain methane. So this presence of methane, how much is there, will give us some clue regarding whether there are other life forms. We do not know whether these life forms are human beings or like that. So this photosynthesis thing, these stars are, the other stars are also capable of giving out light. And among all these exoplanets, there are certain planets which are there in the habitable zone. So the Earth is having life on its surface because it is in the habitable zone of the sun. So for every star, there is an area or a region surrounding it from here to here distance, which is called a habitable zone. In the habitable zone, mostly it is expected that the temperatures will be conducive for water to remain as liquid. So we cannot say that there are other planets where we can expect that there are other planets where there will be life. But until now, we are not able to decipher the details. We don't know which all planets are there. At least out of these 4,000 exoplanets, scientists have stumbled upon maybe 4 or 5 of a habitable zone planets which are having analogous conditions to that of the Earth. So it may be possible to have life in these exoplanets, and having the factor that we have only detected only a very few exoplanets. In future, there can be more exoplanets which can be discovered, and there can be more chance that we detect life in some other exoplanets. And about the sun becoming extinct, that is possible within 5 billion years. In 5 billion years, the sun will become a white dwarf. Its outer portion will be expanding as a planetary nebulae. Hope you remember, I flashed some pictures of planetary nebulae obtained from Hubble. So all these planetary nebulae are the end stages of or end condition of a stars like the sun. Sun 1.5 times the mass of the sun. Those stars all will end up as a white dwarf. The central portion will be a white dwarf, and the outer portion will expand into the interstellar space as a planetary nebulae. And this particular limit of 1.4 solar masses for a star to become a white dwarf was first proposed by an Indian scientist, Subramaniam Chandrasekhar. And this Subramanian Chandrasekhar is Indian by birth, but he is an American citizen. He is a very famous astrophysicist. And his theory of white dwarfs is that if a star is 1.4 times the mass of the sun or below, then it should end as a white dwarf. So this is called the Chandrasekhar limit. So we can be proud that the Chandrasekhar limit is regarding the name of a scientist who is Indian by origin. So what I am telling is sun will finally become a white dwarf, and before that its outer portions will expand and it will engulf Mercury, Venus, and even Earth. So we can't say how much time our civilization will be there on the surface of the Earth. Now our existence is challenged by the COVID-19, we know for sure. So we cannot expect that we will be outliving, our species will be outliving until 4.5 billion years further, so as to see the end, or so as to be a part of the end of the sun and the earth. We can't say, but that possibly the end of the sun is like this, and earth will be engulfed by the sun. And I should advise you that we don't get panicky about that, because our lifetime is span is almost like 100 years. And this is going to happen after 5 billion years. 1 billion, 5 billion. It's a huge amount of time.
Okay.
It was a long answer, I know. Yeah.
Thank you.